Okay. Shall we go again? Okay, so welcome back. Just as a recap of what we did yesterday. So we proved, I mean, I didn't state it as a formal theorem, but what we did was actually proving this. So if you have an energy function, which is C2 with bounded second derivatives, uniformly bounded, then for all starting point, there is a small alpha 0 such that for all alpha smaller than alpha 0, this gradient method verifies this. So it doesn't quite converge, but it verifies this. And if you put additional hypothesis, then it does converge. So how do we prove this? So we did this computation last time, except f of e of xn plus 1 is equal to e of xn minus alpha plus big O of alpha squared. And the constant in front of this big O is independent of n because of this bounded second derivative hypothesis. And therefore, if you take alpha small enough, you will have this will be smaller than, I don't know, alpha over 2 times this, okay, with no reminder. And then you just sum this equation and you get this. Okay, yes?
One question. So instead of having bounded second derivatives, is it enough to have the Lipschitz continuous?
Yes. Lipschitz continuous first derivative with uniform Lipschitz constant. Or you can replace this if you want by I mean, this just has to be bounded along the iteration, so there are other conditions you can put. Anyway. So the other thing is that if you have a C2 function in the neighborhood of a local minimizer, and if the Hessian is positive, so this is the Hessian, if the Hessian is positive, then if alpha is smaller than 2 over the matrix norm, which is for this matrix the biggest eigenvalue of the Hessian. For all epsilon, there exists a C epsilon. Do not bother about this; it doesn't really matter. Such that for all x0 in the neighborhood of x star, xn converges to x star, and you have the estimation xn minus x star smaller than C epsilon times, so this factor that we said was the max of 1 minus alpha lambda 1 minus alpha lambda n, okay, plus epsilon to the n times x0 minus x star. Okay, so forget about this epsilon. This is the factor that we had. I'm using the same notation as the one we had yesterday. And the proof of this is simply that it's a nonlinear version of the proof that we did yesterday. And you simply use Banach fixed point theorem, meaning that you write f of x is equal to x minus alpha grad f of grad e of x. Okay, and then you do this Banach trick, which is write f of xn minus f of x star. You do this. You do it's bounded by some constants that you have to take care of times you check this, and this you just check by norm of this, and you just check this by the what's it called, accroissement fini, mean value theorem. Is it mean value theorem? Accroissement fini. Okay, and this the factor is the norm of the Hessian along the line from xn to x star. Anyway, it doesn't really matter. This is technical stuff. What matters is this quantity. Okay.
So the power here is the number n, right? The power not just here.
Here, yeah, this is n. Yes. Okay. And then we said, okay, three things. You don't do gradient, you do LBFGS or something else. You use a line search and you use Pagano-Shake, and then you have a good method. Okay. This is just recap of yesterday. Okay, about this. Now, what we're going to do is we're going to extend this conversion theory and practical issues stemming from it to the case of Riemannian optimization that Eric presented. Okay. So I'm going to, at least for most of today, just look at the sphere, which is possibly one of the simplest manifolds, nonlinear manifolds at least. You want to minimize a function on the sphere. Okay, you want to find the minimum of all x such that x norm of x is equal to 1 of t of x. Yes.
So sorry, I guess you
It's
talked
not
about this last year, but
Yes,
exactly.
okay.
Is there any reason why solving an eigenvalue problem through minimization of the Rayleigh quotient using one of these algorithms would be a bad idea and it's better to do something else?
I will exactly talk about this in 10 minutes. So. The answer is it's complicated. Well, it's not. Okay, well, I'm just introducing this and then. Okay. Okay, so you want to minimize this, or more generally, on a more complicated manifold, you have Stiefel, Grassmann, what have you. Okay. How do you do this? Well, minimization under constraint is tricky. Okay, in general. If you don't know much about your constraint, if you just want a general minimization with constraint, then essentially the methods are more or less based on the Newton, on the combined system with the Lagrange multipliers. So you have augmented Lagrangian, this kind of techniques, and they are not so nice. They're okay, but often you can do better. In the case where the constraints are simple like this, it's often better to treat this as a manifold and use a manifold optimization rather than treat this as a general nonlinear optimization with nonlinear constraints. Okay. So the very simplest algorithm you can think of is you want to move along the sphere, right? So this is xn. And you want to find xn plus 1 somewhere along the sphere. So you want to find your xn plus 1, which is somewhere here. You have to parameterize your manifold in some way, right? So you have to write xn plus 1 is like a parameterization of the sphere to guarantee that you will end up on the sphere. So the simplest thing you can do in this case is very easy. You do some kind of update rule, xn minus alpha d, and you just divide by its norm. Okay, so you're at that point, you move in the direction d, alpha d, And then you project orthogonally on the sphere. You pull back to the sphere. Okay? So this is minimally reasonable. And it will guarantee, it's just a very stupid algorithm. You just do a step and then you guarantee you're on a sphere. Okay? How should you take the direction D? I mean, the simplest thing you could do is to just take the gradients. What is bad with this picture? If you do this, remember what Eric told you this morning. Yes? Yes. At the minimum, not at any point, huh? But at the minimum, if the minimum is here, the gradient will be completely perpendicular to the sphere. What this means is that even at the minimum, this will not be zero. You will still do some work. Okay, it's not too bad. And then you cannot use this to monitor convergence, for instance. And also, it's a bit tricky if you want to do LBSGS or this kind of algorithm. So, say, a simple adaptation is to project onto the tangent space to your manifold at xn the quantity gradient E of x. And this turns out to be exactly the same as this thing turns out to be the gradient, the manifold gradient that I think, no, you introduced the manifold, okay? Okay, so this is a reasonable algorithm. Here, your gradient tells you go here, or minus your gradient tells you go here. You don't want to go here because here it's this is not a direction with a lot of information. So instead, you project here, you go here, and then you go back here. So this is xn, and this ends up being xn plus 1. So this is the projected gradient or the Riemannian gradient, or you want to call it. Okay. In a general setting, this works in exactly the same way, except that your projection step, or not projection, your step of going back to the manifold might be more complicated. Okay, and therefore I'm just going to put a big R here, which is a retraction. Yes.
Could you just remind me of what was the motivation for introducing the projection?
Because this quantity is not zero at convergence. This quantity is zero at convergence.
But xn plus 1 will still be xn.
Yes, but well, so it screws up your line search, for instance, because it's not very competitive. But it's fine. It's also fine if you don't do it, because the retraction will be essentially do it for you. But there are some subtleties where it's for. For gradient, it doesn't really matter. So R is a retraction. So R is a retraction. Is a map from Rn to the manifold M, which is in this case just the sphere. Okay, a retraction is not any kind of map. It has to satisfy at least one property, which is that okay, it's not, you cannot be any map, otherwise this will make no sense. If, for instance, if maybe this retraction, you can say it to be minus x, okay, you can take this point and send it to the other side. So this will be stupid. So you impose the constraints that, for instance, for all, it's called V in the tangent space at x, R of x plus D is equal to x. Okay, for all x in M, this would be equal to x plus D plus O on D squared. So you don't modify to first order, because to first order there is nothing to do. At first order you are on the manifold. If you want, on this example, if you look at x plus V, the norm squared of this, if X and V are orthogonal, the first order expansion of this in terms of V, sorry, this is V. There's no first order here. It's only to the second order that this does something. Yes?
So the retraction is something more than simply renormalizing the vector.
So here, in this case, in the case of the sphere, it's this. But you can also take, there are other retractions that satisfy this. Maybe not easy to come up with other things. But in another example, so if you're on a Stiefel manifold, so remember, Stiefel is the set of X belonging to, I'm going to take big. How did you call this, Eric? No, the N and M. So this is this with X transpose X is equal to 1. Okay. How do you retract? How do you retract an X tilde? I don't know. Which is, you see, it's something that is close to being orthogonal, but is not orthogonal. And in this case, there are several ways to do this because you have to essentially orthogonalize the columns of X star in some way. And there are multiple ways to do this. There are Leudin orthogonalization, there's Gram-Schmidt orthogonalization, there's QR orthogonalization. There are several ways. Okay. Yes.
To find the closest point on the manifold.
So it's like a geodesic. There is, so in this case, it's probably with exponentials. Usually it's with exponentials. But it doesn't really have to be the closest point. I mean, for our purposes, it just has to satisfy this. And in practice, when you implement the algorithm, okay, in my experience at least, it doesn't matter which kind of, maybe Laurent has a different experience. Ah, okay. Okay.
For the convergence, it doesn't matter.
For convergence, it doesn't matter. So here you can do Leudin, you can do QR, you can do Gram-Schmidt. Okay, I'm assuming that you know at least one of these. Maybe not all, but at least one of this. Okay. All right. So that's in a general setting, the Riemannian gradient algorithm. So it's the exact equivalent of the gradient method, but on a manifold, or on the submanifold. Okay. So now I want to address San's question, which is why bother? Because in this case, there's an alternative way of setting the problem, which I think was also a question for secondary or something, which is you can assume that you want to minimize the Rayleigh quotients. Like this, you can set it up either like this or like this. Yeah.
First case, the norm is equal to 1.
Oh, sorry. Yes. Of course. So why choose one rather than the other? A priori, which one do you like better between this one and this one? You like the second one because it's in the constraints. Okay. I like the first one because it's isolated. Okay. Here, you're working on the sphere, so the minimum is here. And also here, but that's fine. Locally, the minimum is unique. Here, this is a minimum, but this is also a minimum. Okay, this is invariant by scaling. So there's no a priori reason to prefer this point to this point. So what it means is that, for instance, on the previous theorem, if you try to apply the theory we discussed yesterday, this will not work. I mean, the theory will not work on this. Why would it not work on this? Yes? Actually, I mean, the gradient might converge to a point, but remember the hypothesis I put, which was very important, it's a non-degenerate local minimizer. I wanted to have this. Definite positive. Positive definite. Sorry, SPD. Definite positive. Definite positive. Always miss this. And this will not be the case here, right? Because I mean, if it was SDP, then the minimizer would be locally would be unique. So here in this direction, the energy stays constant. So this matrix cannot be symmetric definite positive. So the theory is not applicable. So does that mean that the theory is bad, or does that mean that there is something bad? Or a bit of both. Okay, it's not because I did not take explicit care of this of this case in the hypothesis that the theory is not applicable. Maybe I just messed up on my theorem and used a bad proof. Huh? So here, let's look at the gradient method on this. Okay, let's look at the gradient method in both. So there's a Riemannian gradient. So that's on the first formulation. What is it? Xn plus 1 is equal to xn minus alpha, the gradient of this, but the projected gradient of this. Okay, so the projected on Txm of Ax. Do we put a half? Make my life simple? Or no? Let's put a... Okay. So what is the projection on the tangent space? This is simply minus alpha Ax minus, sorry, and this is over itself. Okay, and now what is Ptxm? It's simply 1 minus x. Okay, because if x is normalized to 1, so the projection on the tangent space, remember the tangent space, the xm, this is simply the set of v such that v is orthogonal to x. Okay, and this is the projection onto that space. You can check easily. The orthogonal L2 Euclidean projection. Okay, here just because I'm lazy, but of course this is what's on the top. So here this becomes xn plus 1 is equal to xn minus alpha. Now you make the computation and you find it's ax minus x a x x. And here, of course, this is xn. Here, of course, you recognize lambda n, the approximation at the current stage. And here you recognize the residual, right? Because this is axn minus lambda n xn. So if you are at convergence, this is 0, which is good. This is what Eric told us this morning. If you are at convergence, the gradient is orthogonal to the tangent space, and therefore the projection is 0.
Well, this is xn, right? Everywhere.
Thank you. Okay, so that's Riemannian gradient. Okay, so to our left, the challenger and the tenant du titre. I don't know how to call it. This guy that Manu likes. So the gradient methods on the Rayleigh quotient, let's say. So the gradient of that guy is what is it's ax minus lambda x x over by homogeneity, it has to be x squared. Okay, you can make the computation, it's not hard. And again, lambda x is x x over x x. Right? So the gradient method is xn plus 1 is equal to xn minus alpha xn minus lambda n xn over xn squared divided, sorry, not divided. So it is, in fact, just this. Okay? So it's very similar. It's very similar because if you forget about the normalization, here you see that it is exactly the same, except that here, if the norm of xn is not 1, this is not 1. So if I call this alpha prime n, you see that it's exactly the same as this iteration, except you don't renormalize, and you modify the step size. Okay, so between these two algorithms, you might think you have picked a step size that makes sense, but in fact, this step size is dependent on the norm of x. Yes? The optimal what?
X, the optimal x.
Yes. Yes.
So therefore, it means that in those cases, ax is equal to lambda x, and therefore.
Yeah. So I'm saying I agree that this algorithm will both converge to something reasonable.
We said that even that convergence tends to go there. I don't see this.
No. Here it will not. The convergence. This was something else before. Here it's no. Here it's completely fine. So the only difference between these two algorithms is that the step size is not the same, but the direction is the same. So if you renormalize the iterator of this guy, you will find an iteration which is exactly like this, except that the step size is renormalized to an alpha prime n. Fine. Why bother with Riemannian? Here we see it doesn't matter. If you code this on a computer, it will work fine. Maybe your norm will blow up, but that's completely fine. It will blow. In fact, it does not blow up too fast because the thing converges. So maybe the norm at the end is 10, but who cares, right? So now let's do something fancy. Let's do Newton method. On RQ. RQ is the Rayleigh quotient. Is this? The Rayleigh quotient. You do a Newton method. I mean, we discussed this yesterday. This is a non-constrained minimization problem. So you go ahead and do the Newton method. Can anyone guess what's going to happen? You have a kernel. This is interesting because, in fact, no. So you might think that. So, okay. You might think this will not work because the Hessian is not invertible because of this thing we said that the minimizer would not be isolated. This is true only at the eigenvalues. So at the eigenvalues, the Hessian of this guy will indeed not be invertible. But at any place, if x is not an eigenvector, then this is not obvious. You have to actually compute the thing. But it will turn out that this will, in fact, be invertible. So this iteration is completely well defined
The conditioning gets worse.
as you approach the solution, but it doesn't matter because you will never even get there. So this iteration does not converge to an eigenvector. In fact, this iteration does something extremely funny, which is xn plus 1 is equal to 2xn. You can try, you code it on the computer, you see. If you apply this method to that function, you get this. I'm not picking this up. This is what happens. Okay, and the reason why this happens is I don't have a good reason for why this happens. You compute the Hessian, you solve this linear problem, you say that it comes up to this. I don't have a good intuition for this, but clearly something goes wrong, and the thing that goes wrong is indeed the Hessian is not invertible at the eigenvectors, but at the other points, it's not a definite positive, for instance. It's plus and minus eigenvalues. And then it goes into weird directions. And for this particular case, it turns out that this goes into that direction. Okay? So this is one answer to Manu's question. Why bother with Riemannian optimization? Why not do this? And the first answer is that sometimes there's no formulation like this, and you're stuck with manifold. The other thing is that if you want to go to second order, then this will blow up in your face.
There is a method called the ventilation. You know it?
Is it with the Lagrangian or?
No, that you have the Hessian and then you add the row and the column.
Okay. But
It's often used in quantum mechanics.
Yeah, but when you
is to solve.
so you add the row and the column to add the Lagrange multiplier, probably the extra variable is the Lagrange multiplier. So I would guess in math we call it like augmented Lagrangian or something like this. But I'm not too familiar with Lagrangian methods. But yeah, clearly, I mean, this is another way of solving the problem. You do something like this with the notation of Eric this morning. You grab g of x, and then g of x is equal to 0. And this is n plus 1 equation for n plus 1 unknowns. You solve this coupled in x and lambda. This is probably the augmented Hessian. But this is the thing we want to avoid, at least here. Okay, so second order is bad. Interestingly, if you sit down on a computer and you code LBFGS for this function, it works very well. It works, in fact, just as well as the method I'm going to present, which is LBFGS on this manifold.
Why?
Tell me about it. Make a paper on it. I think it's a very interesting question. I don't know, but it appears to be, and I don't have an explanation. This is very weird, right? Because LBFGS is supposed to approximate the Hessian. If you approximate the Hessian, then you are supposed to go into the direction of Newton, and Newton is crap. So something else happens, and I don't know what. This is a very interesting project.
Yeah,
I don't know if I agree. Well, I mean, yeah, gradient and Newton have been studied, this for sure. LBFGS and CG, this is sort of between. Maybe it has, I have not found anything about it, but maybe I just haven't looked hard enough. It's an interesting question. So, okay, so in practice, so this is one case of optimization with degeneracy, right? This is a simple degeneracy, which is simply the normalization. You have other cases where things are maybe different. So for instance, if you do something like minimize 1/2 of x transpose ax minus x transpose b for x in Rn, and A is non-invertible, So maybe, I don't know, A is something like 0, 0, 0, 1, and B is 0, B, B2. 2, something. So you can think of doing this. It means that your objective function does not depend on one variable. Nothing in the function in the thing depends on the first variable. And you just haven't seen that while coding your maybe you screwed up on the formulation of the problem or something. Then what will happen? Gradient method on this will exactly be the same as gradient method if you had taken explicit care of quotienting out the non-mattering part. Okay. Newton will not work because the A is not invertible. But if you take the pseudo inverse in Newton, which is often implicitly done because you often, when you don't know how to invert a matrix, you take the small eigenvalues and you throw them out. And this will actually work, and it will actually be the same as Newton on the second part. Also, LBFGS will work completely fine. But here doing the pseudo inverse trick will work, here it will not. So it depends if your degeneracy is like straight or curved. So, and you have the same kind of story going on for Stiefel versus Grassmann. If you try to optimize an objective function with a Stiefel optimization, but the function is in fact on the Grassmann manifold because you have some invariance property, then Newton will screw up, but Newton with a pseudo inverse will actually work. So I don't know. I haven't found any general theory. It would be interesting to put up a general theory of optimization with degeneracies. Anyway. Okay on this? So now, if you agree, we study the general projected gradient method. Oh, I forgot to say one thing. References, if you're interested in optimization on manifolds, the canonical historical reference is a paper by Edelman, Arias, and Smith, I think, which is 98, 96 about, and 98, okay, which is called the geometry. Okay, I will not write it, but it's called the geometry of algorithms with orthogonality constraints. And it's one of the first math papers to look at this kind of problems. There are books. There's a book which is called Optimization on Matrix Manifold, but it's very long and very verbose. There's a newer book which is a bit nicer by Nicolas Boumal, which is called Riemannian optimization or something like this. Introduction to optimization on Riemannian manifold or smooth manifolds. Okay, this is more recent, so this is 22, 20, 23. Good, people paying attention. It's shorter, it's nice. Okay. Of course, I'm going to take it to talk about like 1% of that book, but hopefully the more interesting bits. So you see, it's something that has been very much led by applications. I mean, if you see, so in this paper, Arias is a physicist, he worked on DFT and so on. And if you look at the paper, it's really motivated. Edelman is a mathematician. And basically, so he said this in the paper. He looked at a survey on linear algebra users, and some users reported, yes, we use a conjugate gradient to solve eigenvalue problems. He said, what? No. Conjugate gradient is for solving linear systems of equation, non-linear system of equation, but not eigenvalue. But in fact, this is what they did, and so they set out to make a geometric theory of this kind of things. So this is an interesting paper. It's very much application driven. The physicists and the chemists have been using this for way longer than the math people have recognized it. As is often the case in physics. Okay? So we go back to the general algorithm. Retraction of xn minus alpha projection on txn m of grad E of xn. So if you want this guy, it's sort of the Riemannian gradient, you can call it grad m E of xn if you want. Is the gradient on the manifold. Okay? So how about the theory of this? What about the global convergence? What about the local convergence? What about the speed of convergence? Can we do the same theory as we did before? What time did I start again? Four.
It's around
3h45 ou? Sur 3h45 ou 4? 4 heures, ok. Donc I have till 5:30. Okay, plenty of time. Okay. So this is a minus. So remember the two theorems I wrote before. The first theorem carries over without any issue. I mean, you have to make hypothesis on the. So remember the first theorem was global convergence. There is alpha small enough such that the iterates will have the gradient that will converge. This works with no problem. You just have to make the same expansion as before. Okay, this is reassuring. This is a good method. Now the second part was about speed of convergence. You remember, it relied on the Hessian. We needed something like this, and the convergence rate depended on this guy. The question is now, what is the analog of this guy for that problem, for the manifold problem? So what is the Hessian of a function on a manifold? Okay, so the function which is defined on the manifold, you can think of it intrinsically this time. The function is defined elsewhere, but if you think of it only defined on the manifold, you would like to cook up something which is the analog of a Hessian. So the analog of a Hessian should be something like a quadratic form on the tangent space, right? It should be a matrix from the tangent space to itself. So if you remember what Eric told you this morning, he had this condition that the Hessian with respect to x of the Lagrangian was positive. Okay, so that's a strong contender for being the analog of the Hessian in that case. Okay. I'm not going to use the Lagrangian formalism. I'm going to stay in the manifold formalism, but the thing will be the same. Okay, so now we take a small detour. So I want to analyze the convergence properties of this algorithm. So we take a small detour. What's the question of what is the Hessian of a function on a manifold? And here there's a difficulty. So you might think it's easy, right? I take a curve. How do you define the Hessian in the usual way? You take curves, you compute the second order expansion, and that is a quadratic form in the direction. Okay. So here you take a curve x of t on the manifold. Okay. Curve going like this. You take x of 0 is equal to x of 0. X prime of 0 is equal to v. Okay. Now you compute the second order expansion. So f(e) of x of t, this is clearly equal to e of x0. Plus, so here, if you remember what Eric told you, this is grad m e of x0 v. Okay, this is the first order term. So here you can take the gradient without the m. So I told you this is the projection on the tangent space of the gradient of V takes 0. So here you can take either this one or this one, it doesn't matter because V is in tangent space. Okay. This is X. X is a point, V is a vector. It's the velocity of your point along the curve. And V is in a tangent space, so it doesn't matter whether you project this or not. But now what is the second order term? Here there are two terms. 1/2 V Hessian of X equals 0 V. This is a nice term. And the second term is gradient of E, it's 0. Tac tac, contre 1/2, 1/2, X double prime at 0. So here, this is a bit problematic. Why? Because this is not a quadratic function of V. This is not V times something times V. And I cannot use this something to define me a quadratic form that would be a good candidate for the Hessian. Okay? So in other words, the Hessian, there is no intrinsic notion of the Hessian because the Hessian depends on the parametrization of the curve. Here. Nice. It depends on the way the curve or the acceleration x double dots. There is, however, trick, and the trick is the same trick as the one that allowed Eric to state that the Hessian of the Lagrangian was positive, or whether in the other direction, it doesn't matter. The trick is the following. Here, you are taking, so we do not actually care about the Hessian at all points. So in general, no intrinsic Hessian. So you might think, yes, there is. You just take this, you expand to second order, and you will find something. Yes, you will find something, but that something will depend on the retraction. So it's not intrinsic. We do not want a definition of the Hessian that depends on whether we use Gram-Schmidt or QR for orthogonalization. But the nice thing and the good news is that there is a good intrinsic Hessian at the critical points. Okay, because at the critical point, there is a nice thing occurring, which is that this guy, remember, it's always orthogonal to the tangent space. So this thing does not, so this thing is fine. We like this thing. It's a quadratic form in V. This thing we don't like because of that term. But here, at a critical point, the gradient is orthogonal to the tangent space. And therefore, this only depends on the normal component of the acceleration. And this is nice, because if you remember your physics 101 classes, maybe 102, there's something called the centrifugal force, which says that if you have a curve on a sphere, the normal acceleration is not arbitrary. Okay, the acceleration is arbitrary. You can move faster or slower on a sphere, but the normal acceleration is not arbitrary. It's given by A is equal to V2 over R, something like this. And this is the centrifugal force, because you write down the equation of motion, you can see this as a force. Okay. So here I'm claiming that on the sphere, and this is very easy to prove, because you just differentiate x of t squared is equal to 1 in the sphere. So I differentiate this to second order. And what do I get? I will mess this up for sure. So I will get 1 plus x0 v 2 plus plus v squared, but I will also get plus x0 x second of 0. So this is the times t, and this is the t squared, and there's a big O of t cubed. Did I mess this up? Okay, maybe not. There's a 1/2. Okay, maybe there are 1/2 missing. I'm too tired to make this properly. But okay, the point here is that you see this guy has to be 0. So v squared plus x0 x second of 0 has to be equal to 0. Because this has to be true for all t. Right? So this was 0 because v is in the tangent space, so clearly this is 0. But for this to be 0, this relationship has to hold. And therefore, this guy is determined by v. Okay, so when I take this expression, I have e of x0 plus, so here I messed up on the t's, of course, t squared, and plus O of t cubed. Yes. So this is that. So at a critical point, this is 0, right? Because this is in the normal direction, the projection is 0. So this goes away. And I'm just left with 2 terms, which is 1/2 of v. This term I like. And the second term I can replace because now I know that grad E at a critical point, I know that grad E of x0 is equal to lambda times x. If I'm doing this on a sphere. And this is the Lagrange multiplier associated to the constraint x squared is equal to 1. Okay. So here I get plus, sorry. There should be a minus. The minus is going to come from here. Plus the t squared. And here I get t squared over 2 lambda x0 x double dot of 0. So now I can replace this using this, and I get that this is minus norm v squared. And that was my goal, right? Because I wanted something that was a quadratic form in V. So the manifold Hessian, which is a second order expansion here, is equal to what? In this particular case, it's equal to the extrinsic variation of the energy. Minus lambda times identity. Right? Because if you want to write this as a quadratic form, this is V on the left, V on the right, Hessian minus lambda identity. Okay, so this is on the sphere the manifold Hessian, defined as a quadratic form on TXM. You okay with this?
So this is only on a sphere, but I guess you
Yes.
can also define.
So
the
in general,
position
it's
in-
the same story, the exact same story. And in general, this will be the hash. And here, in fact, you see that this is also equal to the XX of E lambda, of L lambda. Lagrangian. You see, lambda is the Lagrange multiplier. So if you want, this is a proof in a special context of the theorem that Eric showed you this morning. I don't know if you are going to do this on a general context or not. Yeah, but anyway, this is the very same principle. It's just this, but you have more Lagrange multipliers, so you have to take care, and there's a bit of linear algebra with kernel of A transpose equal to machin. But the principle is the same. Okay? So with this, you can prove the theorem that Eric showed this morning, that if your manifold Hessian is positive definite, again, it has to be positive definite on that space, right? Not in general. Okay, maybe an example before. So if I take E of X equal to R char T XAX, I get the Hessian is simply is equal to A. This is the extrinsic, the unconstrained Hessian, if you want. And the Hessian, the manifold Hessian, if you want to call it like this, maybe. If X0 is an eigenvector, because otherwise this is not defined. So eigenvector is a critical point of the Rayleigh quotient, right? So otherwise this is not defined, but if X0 is, you can define this as being simply A minus lambda 0. Lambda 0 being associated. So X0 is equal to lambda 0 X0. Defined on X0 orthogonal. Yes? So if, for instance, A is equal to lambda 0, lambda 1, you see that at a minimum, at a local minimum, then the manifold Hessian, what is the manifold Hessian in this case? So it's defined on X0 orthogonal. So X0 orthogonal is just this. So it's just a scalar, right? And what is the scalar? Lambda 1 minus lambda 0. And here you see that, yes? Yeah, so the first one is simply the unconstrained Hessian. You simply look, you take any random point, it might be on the manifold or it might not be, and you look at a variation here. Okay? Here you look at a variation, but you don't take only the term coming from the explicit variation, but you look at the fact that you don't actually go here, you go here. And there's a curvature term, and this term here comes from the curvature term. If you want, it comes from a Lagrangian. So this is the objective function, this is the Hessian of the objective function, and this is the Hessian of the Lagrangian. Okay, so here you see, for instance, that if you are at a minimum of the energy of the Rayleigh quotient, then lambda 1 is bigger than lambda 0. Yes?
So two questions. One, the manifold Hessian that you're looking over here, the generic lambda. Without going into the Lagrangian picture, how do you know that this lambda is supposed to be lambda 0 if you are
You compute, how do you do this? I'm confused now. You just compute the gradients because the gradients, so remember, lambda E is equal to lambda X, so grad E is equal to lambda X, and grad E in this case is AX, and therefore AX is equal to lambda X. So if you add an eigenvector, then the lambda, this is the Lagrange multiplier. And this is the eigenvalue. So at an eigenvalue, the Lagrange multiplier is equal to eigenvalue.
You know that it's the Lagrange multiplier.
Yes.
And then just the other thing, so this, the manifold Hessian, is it defined really on x0 curve, or is it?
Yes. It's on the tangent space. So in general, no intrinsic Hessian, but at a critical point, there's a quadratic form on Txm with two terms, one explicit and one implicit. One coming from the velocity and the other from the curvature.
So far we recovered the thing that we could have found from the Lagrangian formalism. Right?
But how do you prove? I mean, you have to prove the theorem that Eric showed this morning, right? If you admit, if you assume that the theorem is okay, then fine, you can say Lagrangian. Yeah, and also I think it's a way to give some more intuition and some deeper understanding, because it's really an intrinsic thing at the critical point. Because this is a miracle. I mean, so it's not obvious at all. I don't know about you, but to me, the first time I saw a theorem that Eric showed this morning, I thought, no, there must be something missing, right? It's not just the Hessian of Lagrangian. You also have to take care about the derivative of the Lagrange multiplier with respect to x somehow. No? No. It's already included by this magic. But it's deep, right? It's non-trivial. Please, for me. Yes?
Just to be sure, come back to the problem, use the full Rayleigh quotient were in place of the norm.
Yes.
You would agree that if you take the Hessian, you would form exactly this.
If you take the Hessian and the critical points, okay, good exercise. Take P of x with 1/2 x. Compute, so now there's no constraint. Compute the usual Hessian. This will turn out to be at an eigenvalue, eigenvector. Because always, as we saw, it's very messy, but if you compute at an eigenvector, you compute this guy and you find it's indeed is equal to a minus lambda 0 x, but now on Rn. So if you want, there's two parts here. 0, 0, 0, and here is the manifold hashing. So this corresponds to the tangent space, and this corresponds to the normal space.
So there is no x, no, for lambda 0x.
Yes, right. Which indeed correspond to the observation that you do not change the value of this going into the normal direction. So yes, you can do this, but you have to take care about removing these bits by hand. And also you have to take care of the fact that be careful not to do this at a non-critical point.
To avoid this kind of weird redundancy.
Yes.
Norms.
Yes.
So have one coefficient in ourselves.
Yes. It's sort of more intrinsic object. Also, I mean, this formulation, it's fine here, but if you want to minimize Hartree-Fock, for instance, it's more tricky, right? You really want to impose the orthogonality constraints. So that was for the Rayleigh quotient. The same holds for the grassman or Stiefel. What do I do now? Okay, maybe I carry on before going to the grassman. We come back. So remember, all this was a little detour. The thing we actually wanted to do was to look at the convergence of this iteration. Exm grad E of xn. We wanted to look at the convergence of this. And now you can guess the results. Okay. So I'm going to attempt to write a theorem like I wrote before about the local convergence. Remember, there was this alpha smaller than 2 over lambda n and the convergence rate with the max or whatever. So there was a matrix involved here, which is the Hessian. And now in the manifold case, what will play the role of the unconstrained Hessian? The manifold Hessian. So the theorem looks the same. So I'm not going to repeat because I'm lazy, but will be 2 over the lambda max of the manifold Hessian. And then the convergence rate will be equal to 1 minus alpha lambda min max of that and that. Okay. So for instance, we can compute something like the conditioning of an eigenvalue problem. Do you remember what we had before? We had the convergence rate. When you optimize alpha, it depends on the conditioning kappa, which is lambda max over lambda min. Yes?
Which Hessian is this now?
The manifold Hessian. When I put a small m
For which critical point?
x star. So the theorem was
We were in the neighborhood of
yes, neighborhood. Maybe I should have been lazy, less lazy. What a surprise. Critical point. Okay. So for the eigenvalue problem, what is lambda min? So if I again E of x equal to 1/2 x dx over xx. No, sorry, not this one. This one, and m is equal to the sphere. So for this case, what will be lambda min? So if I have A as eigenvalues lambda 1 to lambda n, and x star is the first eigenvector, what will be lambda min and lambda max? It's the Hessian, it's the manifold Hessian. And remember, the manifold Hessian is A minus lambda 1 restricted to the orthogonal of x1, and therefore lambda min will be equal to lambda 2 minus lambda 1. I cannot pick lambda 1 because lambda 1 is not in the allowed tangent space. And lambda max is equal to lambda n minus lambda 1. Okay. So what is the good notion of a condition number for the eigenvalue problem is the ratio of this over this. You see the gap, famous and dreaded gap appearing. You know, right? The gap is an important thing for many properties. Yes? So now, either I prove this or we go to Grassmann. Do I want to prove this? It's sort of easy. Well, it's a bit of computation. You just have to expand this to you have to apply the Banach fixed point theorem. So you have to linearize this equation near a critical point, and then you have surprises, and you have the same kind of surprises as you had before with the acceleration. You get something, and you get that result. But hopefully, this should not be too surprising. Yes? Yes?
Question, is it possible to use this the manifold Hessian to define a Newton?
Yeah, of course. I mean, yeah, yes.
Or you going to
No, I can talk about it now. So the
Hessian, which is closest to the point that you're.
so you pick a Hessian. So the Hessian, I mean, so it's a bit tricky to know how to do it. I mean, okay, the simplest thing you can do is there are multiple Newtons, but you can take this iterates. You can pick this and make linearize this, in fact, exactly like the proof I was talking about, and try to make this 0 in the Newton approximation. But this will depend on the derivative of this retraction, which might be nasty to compute. But you do not actually. So when you do this computation, you find out that you've got derivative of this that you don't want to compute. But you do not actually have to compute. You just have to compute the terms that will contribute. So maybe a simple version of the Newton for this one. It's going to break my heart, but I'm going to say it's a Lagrangian version. So, is there a better way? Probably. But you can do it with the Lagrangian. So you define the Lagrangian, but even with the Lagrangian, there should be some ambiguity. But okay, so you have your Lagrangian x of lambda. So either you do it in an augmented way, so you do the Newton method on grad E is equal to lambda grad G, and G is equal to 0. So either you do that, or you do the optimization Newton, and the optimization Newton is it's not minimizing the Lagrangian, but it looks like minimizing the Lagrangian. So you do like you minimize the Lagrangian, but you don't. But you do find the lambda XX, and you divide by this. So yes, I mean for sure you can do Newton on. There are many formulations. All of them are asymptotically equivalent. So the nice thing about Newton is that if you've got something that converges quadratically, you call it Newton. If not, you call it something else.
Here in this, you just pick the current guess you have for lambda.
Yes.
So it's just basically taking the manifold Lagrangian and changing
Yes.
the.
But the manifold Lagrangian, you see, is not well defined if you're not
but
autocratically controlled.
nothing stops you from
But for
taking the value of lambda.
Yes, but you have to get a value of lambda, which is not even in this formalism, it's not trivial. You have to update the Lagrange, the lambda somehow. But yeah, there's a whole literature on this. So either from that side, sorry, the point of view I raised, or from that point of view. And you can do LBFGS. You just close your eyes and you do it. You know that seriously. I mean, you take the LBFGS that you had before, and each time you've got a gradient, you project on the tangent space. Because the problem is LBFGS, you have to compare, or even CV. You know, you have things like this. which was equal to which should be equal to the extend. Problem is that if you are in a manifold context, this does not mean much because these belong to different spaces now. This belongs to the tangent space at n, and this belongs to the tangent space at x minus 1. So you have to match them somehow. So either you do it properly with something called parallel transport and so on and so forth, or you do it stupidly and it works. Okay. So that turns out to be a very efficient method in practice, LBFGS on the manifold. Or CG, or what you prefer. Anything you wanted to talk about before moving on to Grassmann? No, I think I'm fine. Okay. So we do this with Grassmann. The same, but more complicated. In particular, we can ask what is the Hessian problem. So Stiefel, Grassmann, I told you about it a bit. So Stiefel is matrices with orthogonal columns. Grassmann is set of subspaces. There are many parameterizations for the set of subspaces, but in quantum chemistry, what people like is the density matrix. So P with P transpose P. So how should I call it? P, D, how do you call it, Eric? C? No, C was the Stiefel. So C is NB times N.
Usually I use, well, as you want.
Okay. Allez, P. So P is equal to C transpose. P, D, gamma. P is nice. Allez. Adjugé. Donc, P is the projector onto the orbitals. So this is the NB times NB matrix. Okay, so the density matrix satisfies P transpose is equal to P, P squared is equal to P, trace of P is equal to N. So what it is saying, so this is a self-adjoint emission matrix. It is idempotent, so the eigenvalues are either 0 or 1. And its trace has to be equal to the number of electrons in your system. Fine. This is a density matrix. So this, the set of all P such that this, I'm going to call maybe somewhat abusively the Grassmann manifold. Okay. Grassmann manifold is something defined more intrinsically, but this is a specific parameterization of the Grassmann manifold, the set of subspaces of dimension n. Yes? Okay, now how do we go about doing optimization on this? We minimize E of P with P belonging to M. So the first thing I have to do is I have to compute the tangent space of this guy. It's a useful first step. What is the tangent space? So the tangent space of a submanifold is defined by a set of constraints, is defined as the kernel of the derivative of the constraint, if you want, which is a very fancy way of saying I write P plus delta P, I expand this to first order, and I see that it has to satisfy the constraint. Okay, so this transpose has to be equal to that. So clearly delta P transpose has to be equal to delta P. It's not a surprise, this is a linear constraint. This says that the trace of delta P has to be equal to 0. This is also a linear constraint, it's fine. And this is more interesting. P plus delta P times P plus delta P is equal to P plus delta P. You expand, you neglect the second order term, you are careful that these are matrices. So they don't commute, but P delta P plus delta P P is equal to delta P. And look at the first order. And this defines delta P. I don't know if you like this notation. Delta P is not delta times P. It's delta P. It's a variation. You don't like this one, this notation? You do? Okay. I like it because it frees you from having to find another letter for the variations, which is very annoying. Yeah. I used to not like it, but I like it. Anyway. Okay, so what does this mean? So if you in a basis, where P is equal to 1, 0, 0, this being the identity matrix, if you want, it's I, it's n, so this is n, nb minus n. So what does this mean? You just take this on the right and on the left, and it means that is there an easy way to do it? When you do the computation, it's not particularly interesting. So you see that delta P has to be of the form 0, 0, something, and something. Okay, you should compute this product. So you set it equal to and you set it equal to 0, and you find that the diagonal blocks have to be 0. So what does this mean? It means that in chemistry notation, these are the I, these are the A, okay, occupied and virtuals, and the delta P is excitation only. It's off diagonal, so it's delta P ij has to be equal to 0, and delta P AD has to be equal to 0. Only the IA and the AI term can be allowed to remain. Okay, and why? Because if you put something here, it's just a mixing between the occupied or between the virtuals, and it does not change the density matrix. It does not change the subspace. Okay, so that is the structure of the tangent space. The set of matrices that satisfy this, in other words, is a set of matrices that satisfy this. I'm assuming you are familiar with the I and A notations. Otherwise, I are just these indices and A are these indices. All right. So already we find some familiarity with the Hessian before, because if n is equal to 1, you see that you only have delta P A essentially with A bigger than 1. So you see that these belong to the, it's like we had before with the X, right? It will belong to the orthogonal of the X. So here, this is the orthogonal of the X if you want. Okay. So that's our tangent space. What does the Hessian look like? Well, this is the computation that is a bit annoying. So we want to look at the manifold Hessian. So there are several ways to do it. So maybe to be a bit more concrete, let's say I want to minimize trace of HP under constraints is equal to M. You know the solution to this thing? What is the solution to this thing? This is a non-interacting set of electrons. How do you minimize the energy of a non-interacting set of electrons? Just occupy the lowest levels. Okay. So the solution to this we know. Now, how do we prove actually that this is the solution? We have to compute the manifold Hessian. So there's one term which is not going to give me much trouble, which is the extrinsic Hessian. Why? Because this is linear, right? So this is 0, identically. But The other part, the curvature part, is non-zero. So how do you compute this? Well, you do exactly the same as before. You compute this. And then you find that there's a term, so this is E of P0 plus P of 0, sorry, plus the gradient. The gradient here is just H times P prime of 0. At a critical, oh, maybe I should have started, I should have done the critical points first. No, you didn't do this, the critical points.
Just to make sure I understand. If I'm following this station of the energy equals 0, of the frequency equals 0,
Yes.
you said it's the addition outside?
Yes, the outside Hessian is 0, but this is non-zero. Just because, I mean, this is linear in P, right?
Yeah.
So,
Okay.
okay, so first order condition before doing this. The first order condition is what? It's that the gradient has to be orthogonal to the tangent space. What is the tangent space? It's the set of matrices that look like this. What does it mean to be orthogonal to all the matrices that look like this? It must be block diagonal. Right, orthogonal to T M. So grad E is simply M, sorry, H. So to be orthogonal to matrices that look like this, orthogonal for the inner product between matrices, right? It means that necessarily it must look like this. So this implies that H must look like this. And then you see that it must mean that H and P commute, and therefore that P is made up of eigenvectors of H. Right? Hartree-Fock equations, if you want. Okay. So maybe I just skip to the result of the second. So the second order, you have to make this. Then you find all the terms. The terms depend on the second variation, so on P second of 0. Now you play this game, but now up to second order. And up to second order, you find something very interesting, which is that, so now if you expand this to second order, you find delta P squared is related to something, right? No, sorry. Well, you do this, but with a second variation. Up plus plus is equal to plus. And then you equate this to second order in the exact same way as we did before for the sphere. And then you find the next relation, which is that the delta second P. So here, you find that P second of 0 is something, okay? But these parts are more or less arbitrary, but this part here is not arbitrary because this part is in fact the projection onto the normal plane, right? So the occupied block of the second variation is determined only by the P prime in the exact same way as we had before for the sphere. And this is what counts for the term that's coming next in expansion, which is trace of H times P second of 0. Okay, and now you express this term only as a function of t prime. That gives you a second order condition. In the second order condition, so what is the second order condition? The second order condition, remember, is a quadratic form on the tangent space, CPM. Meaning on all matrices that look like delta P IA. Okay? So if you want a matrix or a tensor representation of this, what does a quadratic form on this look like? It's a thing with 4 indices, right? And what does it look like? It looks like some represented by IAJB if you want. This will have some expression, and maybe you can guess what is the expression. If you try to think by analogy with the sphere. So by analogy with the sphere, I and J were just one because there's only one occupied orbital, and A and B are the possible excitations. And so in the case of the sphere, remember, it was the lambda A minus lambda 1. So here, we should have something like lambda A minus lambda I. And here, we put a delta IJ, delta AB.
Here, the lambdas are the
Eigenvalues of H, with the usual convention that the I are occupied and the A are virtuals.
Here you work in the orthonormal basis.
Yes.
So because you could also use the non
With the S, yes, you could, but it's just more annoying.
Once you use the lambda.
Yeah. No, it doesn't matter much. So again, you see that at minimum, this quantity have to be positive for A virtual and I occupied. This implies the Aufbau principle. Okay, so this was for this very simple problem. What happens if you do Hartree-Fock? If you do Hartree-Fock, you have this term, but you also have another term coming here. And that complicates business. Yes? Okay, in particular, the Aufbau principle is not obviously satisfied here. In fact, maybe sometimes not. Okay, so that's the second order condition. So, so again, we find some nice interpretation. For instance, if the gap is very small, then, okay, forget about this. If the gap is very small, this operator will have small eigenvalues. So small, if you want, modes that are very soft, and that will lead to bad convergence. So that's one interpretation. Another interpretation which is nice is you can express the Jacobian of the SCF. So you can analyze the SCF method, so the self-consistent field method that works by diagonalizing the self-consistent, the effective Hamiltonian, the Fock matrix, and then iterating. You can analyze this method in the same framework using the same kind of operators. And so you can relate the convergence properties of the minimization method to those of the SCF method. So if you're interested, we do this in a paper with Gaspard Kemlin. Okay, so that's not the first author. The first author is Eric. and I'm somewhere KL, which is 20 thereabouts, okay, which is a minimization and SCF. You can find it easily. So we use this formalism to make some conclusions about the convergence of methods. And that's pretty much all I wanted to say. There are questions? It's okay?
Right.